Okay, so in this class of elements, and then after that, we'll see some examples of these circuit elements. And then I'll even bring up some past exam paper questions so that you see these elements when they show up in papers or in tests or assessments. Now, we are looking at these because they are a building block to the circuits that you guys are going to be interacting with. So they are going to be helpful in actually creating these elements. Now, there are two types of circuit elements that you guys want to pay attention to really. And you can have what we call passive elements. So you can have passive elements, and then you can also have what are called active elements. Now, from active, of course, you know to say it has to do with something that is working, that is literally doing an action. And in this case, the action is in terms of generating energy. So active circuit elements generate energy. And these, you can look at them as sources, for example. So these generate. So they generate electricity or they generate energy. While passive elements, these do not generate anything. And instead, they're just part of the circuit. They do something, or let me say they depend on what is happening somewhere else. They just respond to what is happening in a circuit. So these are passive elements. Good examples of passive elements are resistors, for example. So these are good examples of passive elements. Resistors, for example, just respond. A good example of a resistor is a bulb. If you have a bulb in a circuit, you know to say a bulb just glows, gives out bright light whenever electricity is passing there. So it doesn't really generate energy on its own, but it responds by giving out light whenever electricity is passing through it. So it is a passive element in the sense that it doesn't generate its own energy. Instead, it receives and then converts. So active elements, for example, like a battery will have energy inside, and then it will generate that, or it will supply that energy to the rest of the circuit. So basically, this is the difference between a passive element and an active element. Okay. Now, apart from these two, perhaps before I move on, are you guys okay with that part? Are you okay with passive and active?
Yes.
Okay, great. So apart from the passive and the active elements, there are types of circuit element that you guys perhaps need to understand. Okay, someone trying to join us. Let's see who is joining us. Okay. Okay. The most important, for example, or perhaps that we are going to look at in terms of active elements here, we're going to look at voltage and current sources. So these are going to be the most important sources that we're going to look at, the voltage sources. So these are going to be active sources, and they are generating. One is going to be generating voltage, then the other is going to be generating energy in form of current. Now, these two also come in two types. We're going to look at those types in detail so that you guys are able to distinguish them. They will be either independent. So when looking at voltage and current sources, they can either be independent or they can be dependent. So we're going to understand exactly what a dependent source is and what an independent source is. Now, before we go on to look at independent or dependent sources, what they are, let's start with a voltage source. So these are just going to be basic. You guys have done these before. So of course, if you find a circuit element where you have something like this, and then you have a plus and a minus one side, and then this is connected. So the purpose here, this just shows a part of a circuit is connected this side and that side. But all we're looking at is this symbol here. So this is a circuit symbol for a voltage source. And then if you're dealing with a battery, of course, a battery would be this same symbol, but instead of this, you're going to have cells. So the cells, you're going to have a long bar here, and here, of course, I've drawn this with 3 cells. So again, someone else trying to join us. So I'm going through this part rather quick, thinking that maybe you guys already know this, but if I point out something that you perhaps do not know very well, or maybe you want me to spend a little bit more time on it, feel free to just point out so that I can spend more time there. So here, of course, we have a battery, and then of course we have cells there to just show that this is what you have. Usually batteries are going to produce direct current, DC. No, not direct current. Yeah, they generate direct current when current is coming from that circuit. It's going to be direct. But of course, in this case, it's a voltage supply. But the current that will be flowing here, of course, is going to be direct, DC. For the most part of this course, you're going to be looking at DC current in a circuit. And then it's only towards the very, very end that AC will be introduced. Okay, now with that out of the way, the next one that you perhaps want to pay attention to is the current source. Again, the basic things that you guys have looked at so many times before. It's going to be indicated by an arrowhead. So if you have a circuit like this one, and then you find a circuit symbol where you have this, and then you have an arrowhead either pointing up or pointing down, then you know to say that this is a current source that is being indicated. So again, this is a voltage source, either like that or a plus and a minus. And then this is a current source with an arrowhead in place. Okay. One thing perhaps I should just mention when it comes to a battery here is, again, something that you guys might have done at lower levels is the longer part here, if you're dealing with the battery, will be a positive end, and the shorter end here is going to be the one with a negative line. And then when you're dealing with a current source, it's telling you the direction of current in a line, and in this case, the arrowhead points in the direction of current. So it tells you to say that along this line, current is going in this way. So current will be going in that direction. So this is what you're going to have. Should you at some point assign something else, let's say if this is maybe the current here from the source, this is a 3 amp supply. Let's say this is a 3 amp supply. And then for some reason, you have an element here, or maybe you assign some current that is going in the opposite direction, say I1, that is going in the opposite direction to the direction indicated by the source here. It would then imply that, well, I1 is still the same as what is supplied here, but because they are going in opposite direction, I1 will have to be negative 3 amps to show that, okay, 3 amps is going up, then I1, since it is going down, will have to be negative 3 amps. We'll see more examples where that is going to be applied as we move on. But for now, we're just introducing these circuit elements. So let's move on to the dependent and independent form of these circuits. Any questions before we move to that? The ones that I was writing here for voltage sources, these two, and then for current source, this one here, these are independent sources. This is an independent current source. Same here, these two are telling you that you're dealing with an independent voltage source. So that's what you're dealing with there. Now, with the independent ones out of the way, let's look at the dependent one. Now, the dependent one is going to be the tricky one whenever it shows up in a circuit. So let's understand what it is. The independent ones, you have interacted with them so far. And I'm reluctant to even say what independent here means, because I kind of feel like in the word, in the name already, it's implied. But it will be important for me to actually specify what dependent here is going to mean. So let's look at the dependent sources. Okay. Now, when it comes to dependent sources, let's first understand what it means. See, when a source is said to be dependent, it means that it doesn't really generate on its own. It depends on what is happening somewhere else. Take, for example, these ones that I was writing here. This is a voltage source and it is independent. What we're trying to say there is that it produces voltage on its own without really needing something else to provoke it or to really switch it on. This is a voltage source. It supplies on its own. Immediately you connect it to a circuit, it will supply voltage to that circuit. But when you look at, some applies to this current source. Once you connect it to somewhere where current is needed, it is going to supply current to that line. But dependent sources, on the other hand, depend on what is happening somewhere else. On their own, they cannot supply. For them to supply, a condition must be satisfied. I have to say, they are still active sources. So, as not active sources, they are still active elements. Dependent sources are active elements. So they are active elements as well. But for them to supply, they depend on a condition. Now, let's understand first the circuit symbol. So the circuit symbol, it will mostly be characterized by a diamond, something like this. But there are two forms. If you're dealing with a dependent current source, so if that dependent source is supplying current, then it's going to be associated with an arrowhead, either pointing up or pointing down. But if your dependent source is supplying voltage, it is going to be noted with a plus and a minus. So this is what you're going to have. So this is a dependent current source. So it is supplying current. And this one here is a dependent voltage source. So just by looking at the symbol inside your dependent source, you can conclude if it's a dependent current or a dependent voltage source. Are we okay with that part? The first thing that you need to keep in mind here is we're saying that a dependent source depends on what is happening somewhere else. Consider this circuit here where you have resistors R1, 2, and 3, R1, 2, and 3 there. And then we have a 10-volt supply here. And then we have a dependent source here. Currently, I haven't shown to say this is a dependent current or dependent voltage source, but we're just saying that we have a dependent source there. Let's say this is a dependent current source, and let's put a current direction there to say it's going downwards. And to show that it depends on something, I can say that the voltage value here, it's 2 times I. Now, what does this mean? It means that the current passing through this dependent source, or this line here, or the current supplied by this dependent source, depends on the current passing through the resistor R3. So if the current passing through R3 was, let's say, 2 amps, it means that the current coming from the dependent source will be 2 amps multiplied by 2. If the current passing through R3 was, let's say, 5 amps, it will mean that the current supplied by this dependent source will be 2 times the current, which is 5 in this case. So in this case, we see that the current supplied by this dependent source depends on the current passing through R3 there. So this is why we're saying it depends on what is happening somewhere else. Now imagine if R3 here, the current passing through it was 0. If no current was passing through R3, it will imply that this is now 2 multiplying 0. So meaning that the current supplied by the current source there, the dependent current source, will end up being 0 amps. So it depends on the current passing through R3 there. So this is how it works. Now let's look at it if it were a dependent voltage source. Again, this could have been, it can be something, anything really. You can even say that this is, you have maybe a plus here and a minus there. And then you can say that maybe this is, I can even say I over 2. So in this case, you have I over 2 there. So again, this, by looking at the symbol that we have here, this is a dependent voltage source, but it depends on the current value I. Again, the current value I is the current passing through I3. I'm not saying that there will always be, if it's a current source, the 2 will be up, and if it's a voltage source, the 2 will be down. No, no, no. Here I'm just giving this for practice sake. This would have been 4i, 25i, just anything really. All I'm saying is it depends on what the value of I is. So this is basically how it works. But now consider this case here. You see, as you have seen in the previous case, we had a current source. I wrote it as 2i. It depended on what I is. Here we have a voltage source, and I'm presenting it as I over 2, but it's a voltage source. Again, it still depends on what I is. We can still have a case where this is 2V. We can still have a case where this is V over 2. We can basically have any combination. All in all, we should see that we have 4 possibilities when it comes to dependent sources. Here, of course, I'm saying that they are all multiplying by 3. It's a dependent source where whatever the value of 3 is tripled, whatever the value of I is tripled, and so on. But what I'm trying to say here is when it comes to dependent sources, there are 4 possibilities. And the 4 possibilities are, firstly, provided you have an arrowhead, it's a current dependent source. An arrowhead in a diamond, this is the dependent current source. And these two are dependent voltage sources. But when you look at the first one here, it's a dependent current source, but look at that. It's controlled by a voltage value. So this, in most cases, will be called a voltage controlled. Since this is a current source, it will be a voltage controlled current source. And when you look at this one, what controls it? It's being controlled by a current source here. But what is it? It's also a current source. So we can say this is a current controlled current source. So CCCS. So this is a current controlled current source. And how about this one here? These two are now voltage sources based on the fact that we have a plus and minus inside. But look at the first one. It's being controlled by a voltage source. So because of that, we can conclude that this is a voltage controlled voltage source. So I hope you're getting what the abbreviations they are meaning. In the same way, when you look at this one here, it's a voltage source. What is controlling it? It's a current source. Or it's a current, not a current source. I'm saying it's being controlled by a current. So we can call it a current controlled voltage source. So in case you end up seeing these abbreviations, this is what they mean. Voltage controlled current source, current controlled current source, voltage controlled voltage source, current controlled voltage source. Are we okay with that? Now let's try to find these circuit symbols in some past exam papers and in some test papers. Okay, so here we have some past exam papers and some past test papers that I've already found here. Some of them have solutions, some of them do not. But all I want you guys to see is want to find these circuit symbols so that you can just see how they are incorporated in circuits. So look at this one. Here we have resistors. This is just a current source. Of course, that's a current source as well, direction indicated. And then, of course, what else do we have? Are we going to find the dependent one? There. Can you guys identify this one? So what is this one? Yes. V C V S. Yes. So this is a voltage controlled voltage source. So yes, that's a voltage controlled voltage source. In most cases, you might not even need the first two, provided you know that it's a voltage source, you can easily handle it, treat it as a voltage source. But you might encounter a part where you need to know to say it's a voltage controlled. So don't perhaps forget that. Let's see what else we have. Okay, so look at this again. See that? Again, here you have that's a diamond with an arrowhead there. So here we have a current dependent current source, and this is current controlled. Anything else? Like a few weird symbols. Those are going to be inductors later. Okay, so see if we can find more weird things. Not really from test one. Yeah, it's okay. Test one as well. Okay, so I know dependent sources are not that common in test one, so perhaps that's not really ideal. We have an exam. Can I find an exam? I did search for test. Let me get exam. Okay, there. Okay, so there we have this one here. So that's voltage. That's a voltage dependent source, current controlled. Here, current controlled, current source. So basically, we're just seeing them here, nothing fancy. We'll see how to treat them later on when we find them now, when we start solving these circuits. Any questions? So look at this example. In our example, we're trying to calculate the power supplied or absorbed by each element. Now, the circuit that we have is this one. Now, how do we approach this? Well, this is actually very simple. There are no calculations or weird calculations that are necessary here. All we're going to use is the formula for power that we pointed out, I think, in our previous triple E class. We did point out to say that power in electricity can be looked at in terms of voltage times current. And look at this. For most of these circuits, we're actually given what the voltage is for each circuit element and the current passing through that circuit element. Let's take, for example, the power P1. The power P1 is the power from this. And when you look at this is a source. So when you look at this is a source. And for a source, how do you calculate power? The voltage associated with this source, this is supplying 20 volts. So I can say here, the first one is P1. We have a 20 volt being supplied, multiplying the current passing through this. Now, when it comes to the current, all you need is the branch, or basically the line where that source is a part of, which is this line. So what is the current in that line? Well, look at that. It's a 5 amp current passing in that line. So you have 20 by 5. So when you multiply these, you're going to end up with 100. And then what is the unit for power? Power is measured in watts. So you can look at it like this, but you need to understand one thing. There are two things. You see, some are supplying power, while other elements are absorbing power. So distinguish those that are supplying from those that are absorbing. In this case, you know to say that resistors will absorb power. So therefore, power absorbed is going to take a positive symbol, while power supplied is going to take a negative symbol. In this case, this is supplying, so it is going to take a negative symbol. And for safety, if you want to just be uniform with your work, you can actually just look at it to say that, okay, in this case, the current when passing in this line, you can look at it to say the current actually approaches negative first. So this is going to be negative through this. You're going to have, you can write this as -5 here. When you multiply, this will give you 100 watts. And when you look at this one here, for this resistor, notice that using that trick, actually it works. Because for this resistor, the current approaches the positive terminal first, meaning that here it's going to be plus. Now basically all you want is resistors absorb, so positive, sources give out, so negative. Okay, so this is going to be positive first. So for P2, I will have P2 is equal to, so you need to find the voltage associated or the voltage drop across P2, which is 12 volts. So you will have 12 volts there, multiplying the current passing there. In this case, the current reaches positive first, then going to negative, so plus, and it's still the 5 amps passing through P2. So you still have plus 5, multiplying 5, I mean, and then you multiply this, you get 60. Again, the unit for power is the watt. P3, where's P3? P3 is down here. Again, the voltage drop across P3 is 8 volts. So we're dropping 8 volts there. The current passing is positive or negative. It's finding positive first. So we have a plus. The current finds positive first. So we have plus. But what is the current passing there again? It's a 6 amps that passes through the 8 volts. So we have plus 6. When you multiply these, you get 48 watts. So that is what we have there. Now we have P4. So P4. And for P4, how do we find it? Well, it's really pretty much the same. But we need two things. We need the voltage drop here and the current passing through it. Well, because this is a current source, we can easily say that the current passing through that line is the same as the current supplied, which is this. But what do we have? You see, for a current source, when you're given a current source with an arrowhead like this, it will be positive at the top and negative at the tail. Positive at the head, negative at the tail. So we see that this is positive here and negative here. But look at the direction of current in this line. The arrowhead indicates that current is going like this, meaning current was coming like this and current found this first. I hope you're seeing that. Current found the negative first, implying that here we are multiplying whatever the voltage is with the current in the branch. The current in that line is the current supplied by the dependent current source. And again, this is a dependent current source, so it is supplying current. So meaning we are multiplying that with 0.2 multiplying I. But again, remember I did say that we're finding it negative first. So this value has to be negative. So what is the voltage? That's the trick now. That's the tricky part. We know the current source supplies current, but what is the voltage difference across its terminals? Well, here you have to recall the trick about elements in parallel. See, if you have two circuit elements that are in parallel, so if you have two circuit elements that are in parallel, the idea here is for circuit elements in parallel, the voltage across them will be the same. So if this is, I can even use for resistors. If this is R1 and this is R2, these two resistors are in parallel. Because of that, the voltage drop or the voltage difference across their terminals will be the same. So the voltage drop or the voltage difference across R1 will be the same as the voltage difference across R2. So if, just like for resistors, even if one was a resistor, R1, and then we say this is a source, I can even say this is a voltage source. Say this is a 10-volt voltage source. And then maybe there's other circuit elements here and so on. This is a bigger circuit. Now, these two are in parallel. Provided they are in parallel, the voltage difference across this resistor and across this has to be the same. Since the voltage difference across this source is 10 volts, it means that the voltage difference across R1 also has to be 10 volts. Why? They are in parallel. So, remember what voltage difference is. If I have this as a resistor, the voltage difference means the voltage between this point and the voltage between this point, the difference in the voltages between those 2 points. Now, if I have 2 elements which are connected to those same 2 points, it means that these 2 points will have the same difference. Provided they're connected to the same 2 points, it means that this sees the same difference here and here as this one will see. So they will be exposed to the same potential difference across their terminals. Is that clear? That description will be so helpful going forward. It will keep on showing up. So here I'm trying so much to explain it, keep even repeating the explanation, but it will keep showing up as we go forward. But are we clear on that?
The last one, terminal.
The last one. Okay. So imagine this. Here you have a supply point, and then here going the other side. And then you have these two. You see, the potential difference across an element, it's like you have to measure the voltage here and then minus the voltage here. That will give us the potential difference across R1. So let's say this is, I think when I'm looking at potential difference, I did say, if you have, let's say this is at 20 volts, and then you have this is at maybe 5 volts, it means that V1 is equal to what? The difference between these two, V1 will be at 15 volts. So this is what we have. But it's like when two terminals are connected to the same 2 points, when they're connected to the same 2 points, what does it mean? It means that the difference in potential for the first one will be the same as for the second one. Why? Look at that. It's like you have this is connected to here. Even this is connected to the same 2 nodes. So when evaluating the potential difference across this and this to find the voltage V1 here, notice that it's the same when doing it for this one, because it's the same 2 nodes. To find the voltage difference V2, the voltage value here will be maybe, let's say, that is 30 volts. Even the voltage value here can be seen as 10 volts. So in finding the potential difference at this point and also at this point, notice that the potential difference will end up being what? At 20 volts, meaning V1 will end up being 20 volts, because that's a difference. Even V2 will be 20 volts. So whenever you have elements which are parallel, it will imply that the voltage difference across their terminals will be the same, regardless of how many they are. Even if I had one line like this and another line like this, then I have elements here, another element here, another element here, and then maybe here I can even put the voltage source. The value of the voltage here because these are parallel, the voltage, this voltage also supply a voltage here and here, which creates a potential difference across these 2 points. Meaning these will see the same 2 points, because remember, this will appear as if it's 1 point. Even this will appear as if it's just 1 point. Meaning that the voltage difference across this will be the same as across this, and it will be the same as across this, and they'll all have this value. Have you got that?
Yes.
Okay.
Sorry, I've got a question.
Go ahead.
So are you saying the voltage value across the elements will be the same as the value of the voltage supplied?
Yeah, you have to get, like, for example, this circuit I've given you here. It's even the same reason why you use parallel connection in households or almost in domestic use. Why? Because it supplies an equal amount of voltage to each element. For example, here it ensures that this is fed. Let's say if this is a 10-volt supply, it ensures that this is fed with 10 volts. If in here this is 10 volts, here this is 10 volts. The only thing that will be different for these elements will be the current that will go through each one of them, because the current will now depend on their resistance value. You get that?
Yes.
Yeah. So they'll be exposed to the same voltage, but what will be different will be the amount of current that will be passing through each element.
Okay.
Yeah.
Sorry, another follow-up question.
Go ahead.
So if you look at the circuit we're using in the question, the bottom is 20%, and it's to be parallel as well.
Yes. You used a good term there. They seem to be parallel. Now, are they parallel? I can point out this. P3 and P4 are parallel, and that is what I was going for. P3 and P4 are parallel because of that. In voltage across P4 have to also be because they are parallel. Based on that, when calculating P4, I will use 8 volts here. I'll come back to your question again. So I'll use 8 volts here. And when I substitute, because this, remember, depended on what I was what? I was 5 on this side. I was 5. So this would be 0.2 multiplying 5. So this would be 8 negative multiplying 0.2 multiplying 5. What is this give us? Is this, what is this giving us? Is 4. What are we getting? Oh, it's the same. It's the same 8. Minus 8, yeah. Minus 8, right? Is it?
Yes.
Okay. We get minus 8. Now that's P4. Now going back to your question, Kondwani, here, P3 and P4 are parallel because of that. We conclude even voltage here has to be 8 volts. Now, you were saying P1 and P3 seem to be parallel. Now the question is, are they parallel? Can someone answer that? They are not parallel. This is the reason why even the voltages across them are different. They are not parallel. Now, for you to see that these two are not parallel, you need to understand what makes elements to be parallel and what makes them to be not in parallel. So for circuit elements to be in parallel, we will look at this when we start looking at series and parallel. But because you brought up the question, let me just answer that. So for circuit elements to be in parallel, they must be connected to the same two nodes here and here. So if I was to connect another circuit element there, then we can conclude that these two circuit elements are in parallel. But if I was to connect something else, not necessarily that. If we, let's say, ended up having something else, I can say that I want to just confuse this, so this is no longer parallel. Okay. If I was to just place maybe another element here and then do this. So let me do this, copy this, and then take it back. So you have to see the difference between the two circuits. Now, yeah, perhaps because these two are series, you might want to say that they can just be added. So let me just confuse it by making this a current source. Okay, like this. And let's bring this. Okay, so look at the two circuits. You see, when you look at these two circuit elements, these two here, these are in parallel. Why? Because they connect to the same two nodes. And let's show the nodes. This line can be seen as just one node. Even this can also be seen as one node. And our circuit elements connect to those same 2 points. This one connects to this. Yeah, that's not too visible. That's correct. This connects to our node, this side and that side. So it connects to that line there that we're saying is one node. Even this one connects to the same line. Now, for it to be a node, there shouldn't be anything between. Whatever element we put between is going to disturb the whole connection. For example, in the circuit below here, you see this circuit, this resistor down here, you can say that it connects here. Well, this one here connects here. This one down connects here. This one connects down here. Well, when you look at the bottom is one node. The bottom, they connect to the same point because there's nothing there. They are connecting to the same point down there. But at the top, they are not connecting to the same thing. Why? Because of this resistor, or not that current source. You see, the current source disrupts the connection here. So this current source connects here and here. So because of that, these two are not in parallel. Do you see that?
Yes.
So based on that, when you look at our circuit here, the presence of this circuit element ensures that P1 and P3 are not parallel. Do you get it now, right?
Yes.
If this P2 was not there, if we just had this, then yes, these two would have been parallel, and it would have been expected that the voltage here would have been the same as the voltage here and the same as the voltage there, because the three now are all in parallel. Do you see that?
Yes.
Okay. Okay, so basically this is how it goes. We have in return figured out what the 4 values for the power absorbed are, and clearly the supply negative means power is being supplied, positive means that that circuit element is absorbing power. So again, negative is giving power, while positive means using power. Okay, so basically that's what we have in terms of our circuit elements. And I think we're going to end here for tonight. Any questions before we break?